Welcome to the last PALS seminar of the semester. We will start up again in spring, but today's lecture is by Ralph Freese, George McNulty, and Walter Taylor, who will tell us about their recent volumes in the series Algebra, Lattices, Varieties 1 through N. George, would you like to take over?
Yeah. Let's see. The occasion of this seminar here is a little bit different than most of the PAL seminars. We're not going to try to introduce new mathematical ideas or show you some new hot proofs and theorems. Instead, we want to show you something about how our project, Algebras, Lattices, Varieties, arose and how it developed over the course of time here. And so this will be a little bit different. You'll see that let's see. The first thing here is I'm going to talk to you a little bit about the history. I pulled out four dates here. 1977 is when our project began, actually. 1980 was the occasion when we first had a really good view of what it would take. 1988 was the year after the first volume was published, along with a lot of other interesting books. And then we're going to skip forward almost 30 years, I guess, until 2018, when we finally met and decided what would go into volumes 2 and 3 and 4. The occasion of this thing is actually that volumes 2 and 3 have just appeared. So it's possible for everybody to get their hands on a hard copy or an ebook. We'll see how to do that a little bit later. But then as we go along, you'll see what happens. ALVN, that's Algebras, Lattices, Varieties 1 through N. We began to call our project Alvin. So if you see something in the web or someplace on published papers, even you can see the word Alvin, and it means our project. Then we're going to do two things. Walter's going to talk about how the story Malsef started continues to give you a little bit of a flavor for what can be found in our volumes. And then Ralph Freese is going to talk about what's the theorems spanning chapter 6 and 11. 6 is the first chapter in volume 2, and 11 is the last chapter in volume 3. It's the commutator in volume 6, in chapter 6, and the Malsef conditions primarily in chapter 6, and the commutator in chapter 11. So that's how the talk will be laid out. So my part is to tell you something about the history. So back in 1977, some of you can remember 1977. Maybe some of you need a little reminder. There was about there are 6 books actually in the field. Paul Cohen's book came out in '65. It was the first one here. It has a kind of surprising model theoretic flavor to it. Birkhoff's lattice theory book, the 3rd edition, which appeared in 1967, that's the year I graduated from college, has a whole chapter on universal algebra. And I think Birkhoff's scheme here, even though he himself had kind of gotten into applied mathematics, Birkhoff wanted to encourage people to work in the general theory of algebraic systems, as we began to call it. Among these books, the one I like the best is Dick Pierce's little book. It's only 148 pages long. That's big enough to cover in you can do it in a semester. It does all of the basic stuff, the isomorphism theorems, Birkhoff's HSP theorem, Birkhoff's subdirect representation theorem, and that's about it, right? But it does a very good job. The book we're most familiar with is George Gretzer's book, which has a lot of partial algebras in it and a proof of the Gretzer-Schmidt theorem. And it has a big chapter on what I would call combinatorics of free algebras. This was work that was largely done by Edward Marszewski and his colleagues first in Lvov and then in Wrocław. Maltsev's book, well, it came out in 1973, but actually Maltsev died in 1967. So the book was completed, but was delayed by, the publication was delayed by his death. Maltsev's book also has this model theoretic flavor to it, and it offers a really nice introduction to the theory of quasi-varieties, something that's missing in all of the rest of those. Bjarne Jansson's book is rather specialized. It's concerning representation problems, so representing groups as groups of automorphisms of an algebra, or lattices as the lattices of congruences of an algebra. It has actually it has a proof of the Gretzer-Schmidt theorem in there. That's what the field looked like. If you wanted to get a book, that's what you had to get, right? And what was the field like, though? Well, the first issue of Algebra Universalis came out in 1971. And there were research centers of intense activity in North America and Europe and the Soviet Union. And I was thinking at one point that I would list some of those, but it seems to me pretty dangerous because there were quite a few of them, and I would probably not mention your favorite one. So I'm not going to say what they are. But there were also isolated but really productive researchers like Kirby Baker down at UCLA, right? And the commutator for congruence modular varieties was actually well developed at that point. We had a pretty good idea what that theory looked like. The understanding of Maltsev conditions was solidly developed. A lot of that work was due to a lot of people, actually. And the first result of tame congruence theory had emerged. Now, 1977 is pretty early for that, but you got to remember Ralph McKenzie was one of our co-authors, so we had a little bit of a lead on that. And then there were regular international conferences. There were some regular international conferences in the 60s, but there were quite a few of them by the time 1977 rolled around. Well, so you could see what we needed to have. We needed to have a new book to address all that new material, as well as older results, like post description of the lattice of clones on a two-element set, which was not in any monograph was available at that time. So that's what we set out to do, right? 1977. Now, let me tell you, Walter Taylor had been writing survey of equational logic, and he submitted the earliest version of this occurs in a conference proceedings from Szeged. He wasn't there, but he submitted the survey paper to the volume, and it was published in the volume. 1975 was that year, and then he and I were corresponding about this. We did this the old-fashioned way with the help of the United States Postal Service. the only way we could do it. We began to talk. So in 1977, I was staying at Walter's house at the beginning of the summer, and we sat down. We said, we got to do this. We got to write this new book. We can start with what you did in the survey, but add some more material. And we began to actually take some of our lecture notes from courses that we'd taken and convert them into chapters in some book that we might be writing. And it was only a few weeks later, maybe not more than 6 weeks later, that we heard that Ralph McKenzie and Don Pagozzi had gotten together to do a similar plan. And so, of course, we contacted them and they said, oh, we'll put all of our work together. So here we had a team of 4 authors in 1977 working on our project. What happened in 1980? Well, the field was like this. There were a couple of more books. Einführung in die allgemeine Algebra by Heine Werner. Nice small book, another 146 pages. Funktionen und Relationen Algebraien by Reinhold Perschel and Lev Kalutzny. That was a book on one of the earliest books on clone theory, actually. And of course, Burris and Sanka-Panavar came out in 1981. We had an early copy of that. We appreciated it as Stan and Sanka had sent us a copy. And but we were happy too, because there was still some stuff that we wanted to put in that wasn't in their book. Their book was conceived as a textbook for an undergraduate course. Ours was conceived as a textbook for a graduate course, so it was more stuff. Also, we knew by then Heinz-Peter Goom had given us a geometric perspective on the commutator, and tame congruence theory was really at our fingertips. We really had the first results there already. So here it was in 1987. The first volume came out. Now, this is the current version. The first volume was published by Brooks and Cole in their Advanced Mathematics series. But in 2018, the American Mathematical Society brought out another printing of volume 1 in the Chelsea Classics in Mathematics series, and that was made me feel really good to have the AMS think, it's a classic. Okay, here's what we got now. Though we got 2 new volumes. Volume 2 and volume 3. And well, you can see that the AMS thinks each one of these 2 volumes is at least twice as wonderful as the first volume, at least if you go by the price. Actually, the first volume is a hard copy, hardback thing, and these are paperback. That's the effect of the pandemic, actually, on the funding of the American Mathematical Society. When the first volume came out in 1987, the price of it was $47. And, so over 30 years or something, it didn't go up by much in price. And in fact, if you're a member of the AMS, you can get it for $42. Or you can get this one and this one for $100 if you're an AMS member. And you can get any one of these or all 3 of them as ebooks. And in fact, the AMS has a program that if you're a member of the AMS, you can get one ebook a year for free as a benefit of your membership. So as soon as I could, I used my one free thing to get an electronic copy of volume 2. And I think Ralph Freese got an electronic copy of volume 3. And next month, I'm getting an electronic copy of volume 3 myself. The nice thing about the electronic copies is that there are lots of links, hyperlinks in the thing, and they work fine. And this is the website for the AMS bookstore. So if you want to get it, you can visit that website, bookstore.ams.org. Here we are. All right. Don Pagozzi withdrew from the authorship of the first volume, thinking, well, he hadn't contributed anything to the volume. And anyway, he was getting interested in algebraic logic and has begun his work as really fantastic work with Wim Block. So you see, here's Ralph McKenzie and Walter Taylor, myself, and this is John Kimmel. He was our editor at Brooks Cole. You can probably see where we are. We're up at the top floor of Evans Hall in Berkeley. Off in the background here is the San Francisco Bay. And we're handing him a hard copy. We're not handing him a flash drive or anything like that, because back then that's what we had to do. And it didn't fit in this box. You can see it, there's a little bit too much. There was a meeting in Berkeley. We'd organized it called the Fine Structure Workshop. Ralph talked about tame congruence theory to us for 5 mornings a week, and Yarda Jezik talked about his work about definability in lattices of sets in the lattice of equational series using first order formulas. So here we are. Now, in 1987, we had a meeting in Asilomar. Maybe some of you remember that. And the authors got together after that meeting. You see, we recruited another guy here. We had to have a team of 4 authors. So we recruited Ralph Freese, who was kind enough to join us. I'm behind the camera, so I'm not there sitting at the table. Walter, Ralph Freese, and Ralph McKenzie. And you can see right here next to McKenzie's hand, a copy of the first volume. And over here, these papers that you see are really 350 book pages that we didn't have in the first volume, but we were ready with. And we could have published the second volume, or anyway, it wouldn't have been the same second volume, but we had 350 pages worth of stuff right there. Yeah, so that's wrong. I did this, I hit the thing wrong. Wait a minute, I gotta click through all this stuff. Okay, what was the field like in 1988? There were a lot more books, right? So E.T. Schmidt's book on representation of congruence lattices, Agnes's book on clones in universal algebra, our first volume, the commutator book by McKenzie and Freese, Thomas Ehringer's book, Allgemeine Algebra, which is distinguished among these books that are not very long. It has a whole chapter on tame congruence theory, okay? And then the tame congruence theory book. And of course, now there were lots more theorems. So at this stage, in 1988, well, I wouldn't say that our field had reached the kind of maturity that say number theory or algebraic geometry has, but maybe you could say it was in its late adolescence. And if you got your hands on these books and maybe a few of the older books, the other books, you were well positioned to just go out and prove theorems. And that's what happened, of course. Lots of theorems were proven. Now, 30 years later, here's what the team looked like. And you can see by looking at our hairlines that we got a lot wiser, right? This is actually in Hawaii. It doesn't look like the Paradise Islands that it actually is, but in 2018, we got together to really finalize what would be going into the next volumes. Now, we've been working seriously, I guess, really very seriously since 2011, maybe, and it turned out that we had a whole lot of things all written and pretty well done. So we were talking about right here what to include and what to exclude in the various volumes. And here's what we had to think about. What to include? Well, we had an idiosyncratic selection of the most important ideas and results. And what do I mean by idiosyncratic? Well, it was the four of us. We had to sort of agree, we wanted to get the best stuff and put it in there. We wanted the big results, not only like post result, but Rosenberg's theorem, McKenzie's resolution of Tarski's finite basis problem, J.B. Nation's counterexample to the finite height conjecture. Those could all be fit in volumes 2 and 3. But what we had to exclude was tame congruence theory and constraint satisfaction problems. The dichotomy conjecture recently been resolved at that point, and our idea was to put those in volume 4. We also kind of excluded the theorems that would require ideas or methods that wouldn't be available to people that hadn't completed the first year of graduate study, for example. And this would unfortunately include the Oates-Powell theorem and Ralph Freese's nice theorem that the equational theory of modular lattices is undecidable. We also had to exclude theorems whose proof required too much space, and that applied to Jezik's description of subsets of lattices of equational theories definable in first order logic. Again, a candidate for volume 4. So that's where we were. And I think here's where we pass this thing off to Walter. He wants to start here, I think.
Yes.
Walter, I'm going to click to me. If you want to say, George, the next slide, I'll click myself the next slide.
Okay, but this is a content. Well, okay, I am very glad to be here and welcome everyone here, and a very distinguished audience. I just looked over the list, so I'm probably not going to say anything you don't know, but maybe we can seek some kind of context. Now, there's lots of stuff in this book, these books, you will agree. And I thought maybe just pick out one little story, but a story that goes through all 6 chapters and resonates in various ways. And by that, I mean the theorem of Mainz, which is listed here as theorem 4.141. To get a modular congruence lattice, maybe the best way, or sort of most automatic way, is to apply or to have the permuting congruences. And for commuting congruences, well, they were first known or thought of in group theory, and it's slightly better than group theory, as we know, is the idea of a polynomial P, or a term function P, that's like this one here. I've been touching the screen here, but
I'll try to touch it.
does it? Are you anybody seeing what I'm doing?
No,
Yeah.
we only see what George does.
I see a little fly going around there. Is that George?
Yeah.
Okay.
Next slide.
Okay, so no. Go back, please. There. So this well-known set of equations was kind of interesting, even in this one theorem, but after a while, it became kind of obvious that there were lots of conditions that could be resolved or made sense of or described with something like
Sorry.
well, sorry, I got thrown off there by that. Lots of things that could be put together in this way with the satisfaction of equations, and the satisfaction of equations has to be done not just with any functions, but with functions that come from this variety V that we're talking about. They are term functions of V. Now, I think I should say at this point that one way to describe what we're talking about here is clone theory. And in this book, we have both concrete clones or down-to-earth clones, and we have abstract clones. The difference is exactly like the difference between groups and permutation groups. Permutation groups tell you what's being moved, and abstract groups don't tell you what's being moved. And the only difference here is that we've got functions of more than one variable. And so it turns out that any theorem of this type can be thought of as something that's happening at the level of clones. For example, this says that a certain thing formed in a clone from P and from X, Y, and Z, namely by making Z equal to Y, that something's going to happen with that, they're going to get X. So such things, such classes of varieties or characterizations of varieties came to be called Mal'Sef classes in honor of Anatoly Ivanovich Mal'Sef. So we could, well, anyway, we can move to the next slide now. And it ultimately became possible to say what's meant by such a class. Classes that can be defined with equations in that way are identical to classes that satisfy these 5 properties that have been listed here. I want to say that the first 4 of these properties were discovered or first noticed by George Gretzer in Winnipeg. And he, however, was left open the possibility of a 5th one, which would make it necessary and sufficient conditions. Some of these are sort of obvious, closed under formation of subvarieties. Yeah, if you take a subvariety, you've got less stuff to check, and therefore better chances of everything coming out true. So you're still going to have the class K. Maybe I should more thoroughly mention the 3rd one here, because this brought out something that we don't talk a lot about in ordinary algebra classes at the graduate level. Something here called finite product of varieties. Well, this is one place where if you know clone theory, the whole thing makes a whole lot more sense. We could write down, in fact, in the book, we do write down an axiom set that defines your finite product. So there you are, that's a definition, but it's also true and more intuitive to say if we have a variety A0 and a V0 and a variety V1, if we, first of all, switch our attention to the clone of V0, call it C0, and the clone of V1, call it V1. Now we got two algebraic objects. So we can just form the product algebra then, and then we can come back to a corresponding variety again. So it's variety, variety, clone, clone, product of clones, unpack, and you're back with the product of varieties. George introduced this in this paper, 1970.
George Gretzer.
George, excuse me, yes, George Gretzer introduced this. He didn't phrase it quite the way I did in terms of clones, but you can go read it. And several other people were introducing this about the same time, including our own Professor McKenzie. But I think George is to be credited for getting this concept out there. The fifth one here, well, when you think about it, it's sort of obvious because if you're going to get things in the right class, you're going to have to deduce something about them. And if you look the way Malsefter conditions are defined, that kind of deduction, like many other deduction systems, just grabs a finite amount of information. And that's really what's being said there. So if, for instance, if I want to back up one, please, slide. If you want to check this condition, well, the finite amount of condition of stuff you have to check is you got to check something about P. So it means you got to first know what's the formula for P in V. And that formula, then finite amount of information about that, those, whatever defines P in V is going to be finite. And any deduction of these equations off of that, that's also going to be finite. And so there's the necessary part of that condition. Okay, slide please. And I think in the interest of time, we should move on to the next slide. That was Malsef's theorem. Okay, now there are 2 to the alpha naught Malsef conditions. It's not so clear when you first hear it because, well, there could be a lot of duplication. So we need distinctness of conditions. So here's how I'm going to define one Malsef condition. I'm going to call it M2 for a second Malsef condition. It's going to say this. You take an algebra B from V. You take a proper subalgebra A, then B over 2 is at least 2. B over A is at least 2. So bigger algebra, smaller algebra, one's a subalgebra, the other, then the ratio's got to be of sizes. It's got to be at least 2. Now, I think we could all prove that that's a Malsef condition. It satisfies the 5 things on the previous slide. Now, how do we get one such condition for every real number, or let's say every real number beyond 2? Obvious. Just take what I already defined, change 2 to lambda, and let lambda run from 2 to infinity. There's a whole bunch of distinct, one for every real number above 2. So I hope that proof was understandable. It is to me. So next slide, please. All right, so here, I don't know how much I'm going to say about this, except that this connection of deducing things and looking into these various MALSEF classes. And I must say there's also chapter 6 that I'm not emphasizing so much, but chapter 6 studied every one of these conditions here and every arrow. Arrow meaning, of course, implication in this picture. So maybe some of the single letters, P standing for permutability, C standing for coherence, U standing for uniform congruences. That means anytime you have any congruence anywhere in that variety, all the blocks of the congruence have the same number of elements. Near unanimity means if you have all your, there is a function P, such as P of x, y, single y is equal to x. In other words, a single dissenter, they say, y can be disregarded. Well, so a lot of the sort of crustiness of algebras, the detail is found in many of these things. And I think I'm not going to go. I should say that up here near the top, there's SD meet, semi-distributivity in the wide emphasis on Y, or meet semi-distributive, corollary of distributivity. That's very well represented in our book and chapters about other things as well. And so I'm not going to say more about that now, but next slide, please. And this is, you may want to come back, but this is just lifted out of the book itself, that chart showing, yeah, it's what we need them both up at once. Luckily in the book, you can't ask for your money back. This and the next one are on the same page. So you get to see them in the same way. Okay, I think I won't say any more about that. If we could have another page. We're still in the back of our mind talking about congruence, permutability, and things that can happen with it. Yeah, next one, please. George.
Is that it?
Yes. Thank you. Yes. What I've said here at the top is that the simplicity of MALSEF's two equations. So we're back to that very simple example of P of x, y equals x, and P of xsy equals y. Those two equations I'm calling simple. I hope you agree. The simplicity of those two equations does not necessarily mean that permutable varieties are easy to recognize. And there's lots of good lore, if I may put in one more good word about this book, lots of lore, just stuff we know about this variety and that variety, and sometimes systematic, sometimes completely ad hoc. What we know about a certain variety right in the middle, but yeah, here's x equals x, xy times yx equals y. Those two equations define a variety, which is being called T in honor of Stephen Chance. Very simple, looks very simple. what could be simpler than XX equals X? And the other one's a little strange, but now, is that permutable? In other words, does there exist the right kind of Malsep condition satisfying it? And the answer is yes, that Steve Johns, a mathematician at Vanderbilt, programmed a computer to search for these things. And maybe you can kind of get some mental idea of what would be involved in searching for this. You got to set up all possible lineups of V and W and X and whatnot, all in this way, check every single one of them. And so it's a vast job, but he did it. And he actually found this long, complicated term, sometimes called the chance term now. And it's actually easy. This is the kind of result we're finding. It's hard, but if you found it, it's easy. That's like a magic square, right? You see those when you're in 5th grade, right? And there's no idea of how to build one, but once you've got it, and once you've got it, all you got to do is put in the X, Y there, put the corresponding numbers in the main body of the formula, and just look for instances of that equation and crank it through, and you've got it. By the way, it's one of my favorite formulas in all of equational logic. It's my favorite formula in the entire book. And why? This formula, go home and look at it. This formula is completely right-left, reflective, symmetric. You go and hold this piece of paper in a mirror and look in the mirror, everything works. The parentheses flip the right way, the X flips to an X, the V flips to a V. So I put symmetric letters X, V, and W, and that's to make sure that was true. So it's a nice formula. And it's discovered by Steve Johnson. Then in the next slide, we discover in fact, the difficulty, in a sense, is insurmountable. It's worse than just one case that took John's a long time. It's what's really true here is we're talking about something that cannot be solved algorithmically. I'm not going to read very much of this. We're talking about another class, in this case called P. P is a collection of finite sets of equations. Same was true of K at the start. That's what we're talking about. And we'd like to know how to algorithmically decide this set. And decide the set means decide whether something is in P or not in P. And some very simple and not too difficult conditions seem to be involved. Anyway, it turns out that P is not decidable. I don't want to labor this theorem. I really want the next theorem. The corollary of this is that the set of permutability equations, this congruous permutable things, this set is itself of the type in the previous theorem. Or that's what the proof says anyway, that this consequence or corollary is that bases of congruence permutable varieties form an undecidable set, which means you cannot decide whether something's going to be congruence permutable or not. So this rather simple little theorem of Magdeff has taken us into a kind of exotic world of decidability or algorithmic decidability. And we have a good chunk of that kind of problem in this book. In fact, we have the resolution. We have McKenzie's resolution of Tarski's problem, which goes something like this. Here's one corner of it anyway. You have a finite algebra. You'd like to know is, does that algebra belong to a variety that's congruence permutable? Well, the answer, and you want to know it just from applying some algorithm to the finite tables of operations. And that's,
You want to know whether it's finitely based.
yeah, finitely based. Yeah, thank you.
Yeah.
Okay, so now let's look at the next slide, please. I guess we better move on. This just says that we have one of the lore. Part of the lore we have is this rather exotic variety of Polian from Russia. And anyway, he's got some stuff it's hard to believe when you first hear it, but maybe we can look at the next one, George. Well, that's more about Poland. The next one.
Yeah.
Next.
Okay, that's
So
where
this will
Ralph
be
comes in.
Ralph to speak about. Ralph Freese.
Okay, George, I'm going to click on the share screen on mine. So,
Okay, I'll stop sharing here.
okay. Okay, so desktop one, I guess that's what I want to share. So I share that. And you can see my desktop one, but let's come over here. And okay, are you seeing this big picture here?
Yeah.
Yeah.
Okay, I'm going to go a little bit faster. This one is just a Desargues geometric figure that Bjarne and I used in our proof. Janssen and I proved that congruence modular implies the Argesian law. This is actually what this theorem is, this diagram is a geometric demonstration that Desargues theorem is a theorem if you have more than 2 dimensions. Yeah, it's not a plane. Okay, since I'll move down here. Okay, the next thing is the commutator. In '76, this was Jonathan Smith startled the world, I think, in proving that any congruence permutable variety had a commutator, which is another binary operation on the congruence lattices, and produced another congruence. And here it's specialized in groups to the usual commutator, so that's why we call it the commutator. In rings, it specializes to ring multiplication, ideal multiplication. So that was a big development. But then just a few years later, or just right after that, Hagemann and Hermann showed how to define the commutator in all modular varieties. 2 books appeared. Peter Goom had his geometrical methods, and Freese and McKenzie had a book on the commutator. I'm going to quick say that Peter's book is available from the AMS, and Freese and McKenzie is available from my website for free, electronic version. Okay, this thing, it gave several definitions, and it was not clear how to extend the commutator from modular to all varieties, but there was a big effort to do that. And the thing that won out was the term condition version of the commutator. So I'm going to go on here. Difference terms. A difference term this is something that's championed by Peter Goom. He used these extensively. It looks a lot like permutable. It looks like a Malsef term. This is exactly like a Malsef term. And here, almost a Malsef term. If you have A, B, B, P acts on it to almost equal A. It's theta commutator theta related to A, where theta is anything containing A and B. This was used to prove lots of permutability results in congruence modular varieties. It also is part of Peter's Malsef condition for modular, which is an amalgamation of Janssen and Malsef. Okay, let's go on here. Sorry, doing. Okay, now we're getting to Taylor terms. This plays a big role in the book. We have a whole section on it. And here's one way to define Taylor terms. We have M and N being n by n matrices whose elements are either just X and Y. And then we're going to have a term F, and we want it to satisfy this equation, F applied to M, which means, well, F applied to M equals F applied to N. And this means the ith row. So F applied to the ith row here equals F applied to the ith row of N for each I. Now, the only condition on M and N was that M had to have X's along its main diagonal, and N had to have Y's. And that ith equation that I just mentioned prevents F from being the ith projection. And that's really the essence of these things. So the next slide, here we have Malsef term again. We've arranged it so it's a 3 by 3 square matrix. And we did this by just repeating the first and second equation. So this row is the same as this row. And of course, all the rows here are the same. So we get a matrix like this, and it's pretty easy for anyone to verify that this is correct. But I want to step back and say, what this shows is that if you have a variety which is congruence permutable, then it has a Taylor term. Now that kind of statement is much more general. If you have a variety which satisfies a non-trivial idempotent Malsef condition, any one of those, then it has a Taylor term. So in that sense, Taylor terms are the unique, weakest Malsef class, which are idempotent and non-trivial. So that's what Taylor proved, and that's why they're called Taylor terms. Okay, what's next here? Oh, and then we have this surprising result of Olshak's. If you go back to the definition here, this n being arbitrary means that this is just a Malsef condition as it's presented, but in fact, it is equivalent to a strong Malsef condition, which consists of a 12-place term and 2 equations. I won't go into that because we're running out of time, but I think people are aware of it. So that's in the book too. Okay, I just want to point out an old problem of that has been around for quite some time. Is it true that if you have a congruence uniform variety, is it congruence permutable? And the answer is yes, if it's locally finite, but we still don't know in general. So that's a good old problem. Okay, so now I'm getting into the real part of the theorem spanning chapter 6, which is on Malsef conditions, and chapter 11, which is on the commutator. So we have another one of these diagrams because I got so confused I needed this to see what was going on. Let me just, I'm not going to go into great details, but this one down here, DT, is the class of all varieties which have a difference term. That turns out to be a Malsef class. And Keith Kearns in the 90s proved that if you have a difference term, then the commutator is commutative, which is not true in general. Now, this class that's highlighted here is not a Malsef class. So these two things can't be equal. But on the other hand, what he talked about, when Keith talked a couple of months ago, I guess, If you add TT, Taylor term, to this equation, then you do get an error going backwards. And very nice result. That's brand new. And we're going to concentrate on something similar, not quite the same, but here we have SD join implies SD meet, which when I first heard that this is true, it surprised me, of course, because it's certainly not true in lattices in general. What about the other way? That's false, easy to see. But if you add a Hobby-McKenzie term, which is down here, and you add that to this, then the error goes the other way. So SD join equals SD meet plus Hobby-McKenzie. Okay, so I'm gonna, here we have theorem 621, which is on, as Walter said, this is on meet semi-distributive. So this one, item 1, of course, says V is congruence meet semi-distributive, and then items 2 to 5 give sort of a bunch of Malsef conditions which are equivalent. These are due to Kirby Baker, George McNulty, and Ross Willard. And 1 through 5 are proved pairwise equivalent in chapter 6. So we have a nice theorem in chapter 6. There is some connection with the commutator. It's kind of pretty interesting thing. Being congruence meet semi-distributive is equivalent to being congruence neutral, which just means the commutator is the meet. So that's a bit of a surprise. That's due to Kearns and Agnes Sendry, Keith Kearns. And then there's another thing that's sort of a TCT-like thing. I won't say what I mean by that, but V satisfies an idempotent Malsef condition that fails in every non-trivial variety of modules. Okay, this stuff at the bottom tells you where it is, where these things are proved. And then we have this surfboard picture, I call it. It was made, I can make fun of it. It's actually, George and Walter made this diagram. This tail of the surfboard, which is up here, is all varieties that are meet semi-distributive. So it's a filter in here. Here's the filter of all distributive varieties. Actually, SD join is a filter that sort of, well, see if I get, that is bigger than D, but smaller than this, and it misses F. So it's a filter in here too. This is illustrating that last thing that I mentioned up here, the item 6 up here. This says that you can't have a SD meet variety, which is interpretable into a module. Let's see how I'm doing on time here. I'm probably running out, but I can probably just make it. Okay, I'll say something. Yeah, I'll go on. So we have time for Brian. We need Brian. Okay, so here's the theorem on semi-distributive, join semi-distributive. This theorem always fascinated me. This is, I think, the hardest Malsef condition to prove, and took much longer than all the rest. I don't think it was fully proved and in print until Keith Kearns and Emil Kish monograph came out 2013, I think. Anyway, let's take a quick look at this. V, first condition is V is congruent semi-distributive. That means both. So it's certainly 1 implies 2. It's join semi-distributive. We have this 3A, we have this congruence inclusion here. And this thing, it's slightly new. It's slightly different from the one in Hobby-McKenzie and in Kearns and Kish. It uses, to prove 2 implies 3, you have to use semi-distributivity twice. And this was done by a paper in 2017 by McKenzie and I, but not too much different from what's before. And then once you have this, you get things that look like Janssen terms. Oops. So if I, excuse me, I'll see if I can get here. Yeah, so it sort of says you can go, you get 3 variable terms and you can go from I to I plus 1, given 2 of the variables are equal and a pattern that is just slightly different from distributive. Okay, so if we compare this with the distributive law, the characterization of congruence distributive, it looks very similar. So 1 and 2 collapse to saying V is congruence distributive. For congruence distributive, we also have something like this. How similar is it? Well, the one we have for congruence distributive has the exact same left side, and the right side is almost the same too. We just leave off the first term. So the right side is just this. That shows you how close these are. And so proving, as I mentioned, proving 1 implies 2, implies 3a, implies 3b. You don't see it, but you can guess. Implies 4, and even implies 5. There's an idempotent Mal'Sef condition that fails in the variety of semi-lattices in every module variety. The 4 directions are all pretty straightforward to prove, but getting anything to go backwards is very hard. And unlike now in Janssen's theorem, the hardest part was to take Janssen terms and then prove it was congruence distributive, but it wasn't that hard. And it'd be nice to see if somebody could manipulate these and just give it join semi-distributive, but we don't have that. Doesn't appear to be the case. And so these first 4, this is just what I said before. It's easy to do these things. And it's this one. 5 implies 1 to get backwards is proved in 1174. It's due to Keith Kearns, Emil Kish, and Agnes Sindri. Okay, how am I doing on time here? I think we're just about out of time. And this comes almost for free. And so I'm gonna, I'll let you look at that on your own. It's a beautiful theorem, but it's not a bit. Okay, so I'm gonna pass it back to George.
Okay. So let's pause right here. And, this picture of McKenzie, he's, he's at my deck at an old house I used to have. Anyway, now is the time to ask for questions. So if anybody has a question, we'll try to answer it. Questions? I guess we must have all been really clear. That's nice. Well, in that case, click on the next slide, Ralph.
No.
There you go. Brian, your turn.
My turn. Okay, this was the first of a sequence of songs that I wrote at conferences that we had, and it celebrates tame congruence theory and Ralph McKenzie. And George very kindly asked me to sing it for you. I'm going to sing the verse that's on the screen and the second verse, because the second verse is actually also, is in fact about Ralph. Now I came to Berkeley to hear the good word, an exciting new theory, or so I had heard, till Helen's convinced it's all quite absurd. So Ralph, tell me all that you know. Please sing the chorus. Join in the chorus, sing out the song. It's really quite short, so it won't take so long. Pick up your glasses, fill them again. Let's drink a toast to that congruence tame. Must have a secret, please tell me the way to keep theorems flowing on day after day. Is it that you're still thinking when we've hit the hay? So Ralph, tell me all that you know. Join
Join
in
in
the chorus, sing out the song. It's really quite short, so it won't take so long. Pick up your glasses, fill them again. Let's drink a toast to that congruent name.
Thank you, Brian.
My pleasure.
Yeah, Ralph, hit the next slide.
Okay, let's see if I can, something I keep, there we go.
So this is Blackstone's off of West End, just right across the street from Vanderbilt. Blackstone's is turned into something else now, but it was a fantastic brew pub. Anyway, that's our presentation. Anybody wants to say anything? You want to see anything more? We're willing to say what we can.